Hey guys, this is going to be a really quick video. I only got 16 minutes to film anyway because I need to clear out some space on my phone. Videos take up a lot. But we're going to talk about power today. Basically, this is when you take the idea of work, which is force applied over a distance, and you figure out how much of that force applied over distance you can do in a certain given amount of time, that is power. Okay? Power is the rate of doing work. So if I took, you guys have all done this before. This is not, you've exerted more power at certain times. If you are, if anybody's moved, you know what it's like to carry boxes. Well, if you've ever had to carry a box up a set of stairs or something like that, maybe you've done that, maybe you haven't. I would assume that you have. But if you've carried a wheelbarrow full of dirt, or if you have moved anything in your life, okay, if you do that activity quicker, then you were exerting more power. Okay, so if I take this chair, I know you guys can't see me, but you can imagine I have one of these wonderfully comfortable chairs that I'm sure you all miss. If I take this chair and I lift it up and I move it leisurely from one side of the room to the next, I'm going to be doing a certain amount of work, and you can actually figure out how much power I am exerting based off how much time it takes for me to move that chair from one side of the room to the next. However, if I take that same chair and I run with it, okay, that means that I'm going to exert the same amount of work, the same amount of force over the same distance, but I'm going to do it in a shorter amount of time, which means I'm going to exert more power, and I'm also probably going to get winded because I'm out of shape and lazy. And so by exerting more power, it's going to be harder for me. My heart's going to start to pound a little bit more because I'm requiring myself to do work in a quicker amount of time. So again, down there at the bottom, I love this. It says power equals work divided by time, which is the same as this guy, but it also means that equals force times distance, which is the formula for work, divided by time. Okay, so there might be an example where I give you the force and the distance and the time, and I expect you to find power. And so you have to know that you have to multiply the force times the distance and then divide by the time. But these are pretty straightforward, work over time. So it says doing work at a faster rate requires more power, of course. Okay, you're taxing your engine more when you demand more power from it by causing it to maintain a higher RPM count. Okay, which is the rate per minute, or the revolution per minute rather. So when you get up to that like 5,000-6,000 RPMs, that is your engine is outputting more power than it would if you were at 1,000 or 2,000 RPMs. That's why when you press down on the gas, I know most of you guys don't drive yet, but when you press down on the gas, that's why you get more power. You get a quicker response out of your car. To increase power, you can either A, increase the amount of work done in a given amount of time. So instead of carrying one book across the room or one chair across the room, you can carry two at a time. Or you can do a given amount of work in less time. So you can take that one chair and run across the room rather than walk. You're decreasing the amount of time, thus increasing the amount of power. All right. Dang, here I thought I had, okay, well that's all right. We'll do, I really thought that I had a couple of these, but I guess not. We will do the some example problems after we do the science starter here. This lecture might be a little longer than I thought it was going to be. So I love this science starter because I want you guys to think, hopefully, if you can name a mythical creature. Okay, a lot of you guys, I would assume, I'll give you a second here. Go ahead and name a mythical. You can put it down in the comments if you'd like. Hopefully, you're supposed to name 3. A lot of you guys probably are going to put like a unicorn, okay? Maybe a narwhal. Just joking, that's a real thing. Okay. Maybe you're going to put, I don't know. Here's a local one. The piebald bird. There's a mythical creature here that's local. Whatever you put. A pegasus. Okay, the flying horse. That'd be cool. Okay. Some of you may have put a liger down, but I want you guys to understand that a liger is not a mythical creature. Okay. In fact, ligers exist. For those of you who don't know, a liger is a cross between a tiger and a lion. Okay. This only happens in captivity, of course, because you don't have lions and tigers in the same biome, let alone the same continent usually. So in captivity, however, you can cross, a lion will mate with a tiger. and you can get a liger. And what's interesting about ligers is that they are massive. They're the largest big cats in the world. If any of you guys have been watching a popular show on YouTube right now, I do not recommend it. But if you guys have watched these are highlighted to a certain degree. This animal trainer is actually highlighted. So this guy owns, I forgot his name. His name's Doc something. But he owns a quote-unquote tiger rescue that people can come and visit. And one of the things that he does is in his rescue, he breeds tigers with lions. And you get these massive... Oh, hold on, maybe. You get these massive animals.
Myrtle Beach.
It's not the best quality, sorry.
He successfully combined two species to produce hybrid offspring called ligers. The laws of nature apply to big cats as well as primates. Genetically, ligers are 50% tiger and 50% lion.
Here on my right, we have a Bengal tiger. She's about 1.5 years old, and she's got that bold black and orange striping. And then on my left, we have a young lion about the same 1.5 years old. We can see has a much more tawny pale coat. And obviously the mix of the two right here, with the shadow striping and his bold markings, show us the liger. He's a liger because his father is a lion, his mother a tiger.
That's the baby. Now meet the adult. If you haven't come across a fully grown liger before, then this is the largest cat you're ever likely to see.
Enormous size because the inhibitor growth gene exists in the female lion and in the male tiger. So when you switch around and you get a male lion breeding with a female tiger, creating the liger, you get this gigantic size. Nothing tells it when to stop. In the wild, this enormous size wouldn't necessarily be of any advantage because it would require so much more food. Samson here can readily eat 25 pounds of food in a sitting, where an adult lion can subside on 7 to 10 pounds of food.
The territories of a lion and tiger don't overlap in the wild. If a tiger did meet up with a pride of lions, it's more likely to end up in a fight than romance. So captive breeding is the only way to produce what is the largest cat in the world.
Come here. There it is. Up. There it is. Up. Height. Get close to him.
Ligers show traits common to both parents. For instance, tigers love to get wet, but lions can't stand the water. Samson got his water-loving genes from the tiger side of the family. The liger is living proof that two species who would never meet up in the wild can mate and produce offspring.
Okay.
It works for cats, but how alike are primates?
Hold on. We're going to see if I can
Scientists
go on to the next thing here.
Human DNA when compared to a mix of human and
Let's go back up. Okay, so I wanted to show you guys that because that is kind of a mythical creature, quote unquote, that does exist in the wild. Or it doesn't exist in the wild, excuse me, but it does exist. Back to horsepower, or back to power rather. In the United States, we usually use the term horsepower rather than just watts. Watts are found. They are going to be found, however, on your electronics. So things like appliances will have a watt value. You might have speakers that are, rated for like 300 watts or something like that. And that's pretty common. That's a joule per second. However, a horsepower is equal to 746 watts. And the reason we use that is because at one time we used horses, and so that has just kind of stuck. So if work is measured in joules, then if you mix joules with time, so work or joules per second, then you get, like I said, a watt, named after Isaac Watts. Or no, I'm sorry, James Watts? I forgot his name. But he is the inventor of the steam engine. Maybe James. I can't remember. Somebody look that up for me. Tell me what it is. So let's do a couple practice problems. I'm going to give you guys, like I said, I'm running out of time. I am going to give you guys a worksheet today to practice this. Okay. So it says right here, you exert. Let's go ahead and get a marker. You exert a vertical force of 72 newtons to lift a box to the height of 1 meter in a time of 2 seconds. How much how much power is used to lift the box? So again, power equals work divided by time. And if you want to, you can say power equals work or equals force times distance divided by time. Okay? In this case, you need to look at this particular one because we have a force at 72 newtons. So 72 newtons times a distance of 1 meter. That's not going to change anything. All over a time of 2 seconds. That means that your power output, or your newtons per second, or I'm sorry, joules per second after we convert it, is going to be 72 divided by 2, which is 36, I believe. Mental math, it's going to be 36. And if you just used all of this, it would be Newton meters. Oh, hang on, let's rewrite that. Newton meters per second. But a Newton meter is a joule per second, and a joule per second is a watt. So it's going to be 36 watts that you're actually going to utilize, which is not a lot of power. It takes about 300 watts to go at about 12 miles per hour on a bicycle constantly. It takes a few thousand watts to heat something as simple as a toaster. So to toast your bread, it actually takes a ton of power. All right. The next one here. It says your family is moving to a new apartment. I'm going to leave this guy. I know that it's kind of getting cut off, but I'm going to leave this guy, these equations. In fact, let's put them up here at the top. Power equals work divided by time, which equals force times distance divided by time. Okay? Erase that. It says your family's moving to a new apartment. While, of course, you got to lift the boxes if you're doing that. While lifting a box 1.5 meters, this is going to be your distance. Straight up, to put it on a truck, you exert an upward force of 2,000 newtons for 0.5 seconds. Again, here we have using this formula rather than this. So we're going to say that you're going to go, 200 newtons, okay, times a distance of 1.5 meters. It's in meters, so we don't have to do any conversions, divided by the time of 0.5 seconds. This is my power equation. So if I take this and I just kind of chug away and I get my calculator and I do 200 times 1.5, that gives me 300 divided by 0.5. It's actually going to increase. We're now doing 600 watts. Okay? If you did that faster, it would obviously be a lot larger. It would be a bigger number. Okay? Let's see. Let's do another one. You lift a book from the floor of the bookshelf 2 meters above the ground. How much power is used? And the upward force is 50 newtons, and you do the work in 2 seconds. Again, not utilizing this, but utilizing this. So we're going to calculate that out. Power equals force times distance. So what's the force? You lift a book from the floor. How much power would you use? If the upward force is 15 newtons, apparently this is a pretty heavy book, times the distance of 2 meters, all over the time, which took, how long? 2 seconds. I don't know why it took you so long to lift a book, but, whatever. All right, so we do 15 times 2. That's going to be 30. Divided by 2, we're going to be at 15 watts. I said that really quickly, but it's real simple. 15 times 2 is 30. Divided by 2 is back to 15. So 15 watts is going to be your total power output. All right, we're running out of time. I don't know if we have one more. Yeah, we'll stop here. This will be our last one. Okay. It says you apply a horizontal force of 10 newtons. It might cut me off, so I'm sorry. 10 newtons. So again, we're going to put 10 newtons here. If I can draw them in. To pull a wheeled suitcase at a constant speed of 0.5 meters per second across the flat ground. How much power is used? Hit the suitcase moves at 0.5 meters per second. So we're going to say that it's going to go times 1 meter in 2 seconds. Okay, why 1 meter 2 seconds? Because it's going 0.5 meters in 1 second. So I could say 0.5 in 1, or I could say 1 meter in 2, which is going to give you a total of 5 watts. Okay, because 10 times 1 is 10, divided by 2 is 5. Okay, now, why is that so much less? Because you're pulling something rather than lifting it, and it's already got wheels, so it's got a pretty easy thing. It's got a low coefficient of friction. All right, guys, that is all I have for you guys today. We will, you guys will have a worksheet today to go along with this to try power on your own. Just remember that formula, plug and chug, and you'll be just fine. If you have questions, email me or send me a little message through Google Classroom, whatever you need to do. All right, guys, have a good one.